All right. I'm gonna skip the easy portions. So you said you did arithmetic sequence, right?
Mm-hmm.
Is what we have here. This sequence right here. One. Is this arithmetic geometric? What is this? Neither. How would you classify this sequence right here? Now, it's kind of simple, right? So what you need to know is that for arithmetic sequence, now your teacher might use different variables, but the one that I'm going to be using is this. For arithmetic, you're always adding, okay? You're always adding
Mm-hmm.
or subtracting something that here in this book anyways, they call it the common difference. And the letter we use here is D. So you're always adding or subtracting the exact same number to get from your first term to the second term to the third term. So if you look at this sequence, our first term is denoted by A. A is 2. It's also called T1. The term 1, A is 2. Now to find your common difference, D, all you do is you do second term minus the first term. So here if you do that, you'll see that it's 6. For it to be an arithmetic sequence, the common difference has to be 6 throughout. Is it 6 everywhere?
No.
Where is it missing?
Oh, it is 6.
It is 6. Yeah, it's 6 throughout. They're just adding a plus 6, plus 6, plus 6. So the common difference is 6 and it's consistent. What will be the next term?
26.
26, right? So this is a arithmetic sequence. You're always adding the same number to it over and over again. On the other hand, geometric, I'm going to keep that on the page actually. On the other hand, for geometric, there's only one difference. It's that you're always multiplying. Now it becomes multiplying or dividing. Before it was plus minus, now it's times division by what this book calls. This is Ontario lingo, but I'm sure it's not that different in Calgary. So common ratio, we use the letter R. So you're always multiplying or dividing by the same number. A very easy example is this one. 2, 4, 8, 16, 32, 64. You'll see here that we're multiplying by 2 each time, right?
Mm-hmm.
To get R, what you can do is you can do T2 over T1. That will give you the value for your common ratio R. So if you do that here, you'll see that it's times 2 here all the way throughout. So this is what we called a geometric sequence. Now the difference between a series and a sequence is something like this. 2 comma 4 comma 8 comma 16. That's going to be a sequence, but 2 plus 4 plus 8 plus 16 or 2 minus 4 are a combination of plus minus. These are series. The terms are connected using a plus or a minus sign, okay?
Mm-hmm.
Sequence is essentially, it's a pattern of numbers separated by commas. Or you can call it a set of numbers. Whereas series, now this is going to be a little bit advanced. With a series, it's not just simply, there is a pattern, right? There is a pattern, just like a sequence, but there's more to it. Because you're adding or subtracting numbers, right? Usually what happens is that there's two ways you can go. Either your series will do something that we call converge, which means that you'll get a final answer to the series. Like you put this in a calculator, like what does this add up to? 32, right? So
Mm-hmm.
this converges to 32 if our series only has 4 terms. But let's say there's an infinite number of terms. I'm going to show you the notation as well.
Wait, are you recording?
I think I am. Yeah. Yeah.
Okay.
So let me show you in a notation symbology. This means summation. Okay. Let's say you
Mm-hmm.
have summation x, where x is equal to 1, 2, 3, 4, 5, yada yada to infinity. So you have a set, right? You did set. I don't know if you did it. You can call x as a set of numbers. It's counting numbers. Maybe we even put a zero. Goes all the way to infinity. That's our x. Summation x means the sum of all the x values in there. So to do summation x, what you would do it, you would do 0 plus, this just means a plus symbol. Plus 1, plus 2, plus 3, all the way to infinity. What does that give you? What do you think that gives you? What's the sum of all counting numbers?
Infinity.
Infinity. So that is what we call diverge. You're probably not going to learn about this in your sequence and series class. But with series, you get either convergence or divergence. Okay?
Mm-hmm.
And it has a lot of applications in calculus and integrals and whatnot. And you can even differentiate series. It looks very difficult, to be honest. It looks something like this. And then you have 2e sine theta, something like that. And then the question will be integrate this from 0 to positive infinity. Now we're taking the integral of a series. This is advanced calculus. But for you, all you have to know is that sequence, pattern of numbers, series, they're connected by plus and minus. Arithmetic is when you have to add a number or subtract a number. Geometric is when you multiply or divide by a number. Let's do some examples. 3i, the general term. So here this is an arithmetic sequence. It just says up there, even if it didn't say it, you can see that we're adding 15 or we're adding or subtracting the same number throughout. Let's look at a. So our first term, our a value is 58. What is our common difference?
15.
15. Now there's two ways you can put this into a mathematical notation. The first is called the general term. The second is called the recursive formula. The general term for an arithmetic sequence looks like this. Tn, that means the nth term, is going to be equals to a plus n minus 1 times d. That is the formula for the general term. So what would that look like here? Here it will be Tn is equals to a is 58 plus n minus 1 stays as n minus 1 unless we know what the term number n is, times d, the common difference 15. And that's the final answer for the general term. Now, how does this help you? Let's say for this sequence, the question asks you, well, what's the 100th term? T100 equals what? Well, you could like manually keep adding 15s, right? 100 times, which is dumb. Or you can use this formula here. T100 is equals to 58 plus 100 minus 1 times 15, like that. So that'll give you 58 plus 99 times 15, and the answer, the 100th term in that sequence will be 1543. Okay?
Mm-hmm.
So that's where the general term is super handy. It gives you the term number. Well, gives you the term itself if you have the term number, or also does vice versa. If you have the term, you can always, this is a linear equation, by the way. Arithmetic sequence is a straight line. So this is Tn is equals to a plus n minus 1d. D is your slope. This slope rise over run is d. A is your y-intercept. And n is your x, basically. Okay? And on the
Mm-hmm.
y here, it's your Tn. So using your intercept, your x value, and the slope, you can find the y value. It's very similar to y equals mx plus b. So b plus x times m. D is your m, a is your b. It's a linear function. Part 2 there says the recursive formula. Now you can't really write everything as a general term formula. For it to have a general term, it needs to have a common difference. There needs to be a pattern, right?
Mm-hmm.
But if there is no pattern, how would you write it? Well, the fact is that you can't. You can't come up with a general formula if there is no pattern. In cases like those, we use something called recursive formula, which is it gives you the next term, gives you the next term in terms of, okay, maybe I use a different word, gives you the next term using the term directly before. Now, for arithmetic, it's very simple, but we'll see later when we can't have a general term, this becomes really difficult. So for II, the answer here will be something like this. Your next term, Tn plus 1. Let's say your Tn plus 1 is, we're looking for this term. This is, we know what it is. You just add a 15 to it. It's 103. But this is what we called Tn plus 1. So Tn plus 1 is going to be, and again, this is for arithmetic because we're always adding the same thing over and over again. We're always adding the slope. To go from one term to the other, we're just adding the d value, the slope. You take the previous term that we have, Tn, so that'll be 88, plus d, right?
Mm-hmm.
To get the next term, you just add the previous term. So the final answer for part two, the recursive formula, again, they want the formula, they don't want the term, will be equals to Tn plus 15, like that. Easy peasy, and you're done. Final answer that. Cool.
Yeah.
So the final answer for the previous part was, part A was this one. So this and this. Let's do one more. Let's do a negative one. Let's see if it changes anything. So B. What's the common difference here?
9.
9. So your Tn will be negative 49A plus n minus 1 D, right? Like that. And your recursive, what will your recursive be?
It's Tn plus 9.
Yes. And we're done. This is a very common question. It says determine the 100th term of a sequence with T7 and T13s given. All right. Is this asking us for the general term or for the recursive term? What will be the approach?
The general
The
term.
general term. Yeah, recursive, you're just adding the same number. It's going to take forever. So we're going to be using the general term approach, which says that the general term Tn is A plus n minus 1 D. Now for T100, we don't know A, but we know n. That's 100 minus 1 times D. So our 100th term will be A plus 99D. But we don't know A and D. Once we know them, we'll plug it into this and we'll get the final answer. Now, how do we get A and D? Let's look at the information they've given us. T7 is equals to 465. Using this formula, what does this become? If you replace n with 7, what does that become? You can write down what the givens are, right? So we don't know A and D, so we don't know what this and this is. But we know that T7 is equivalent to A plus 7 minus 1 times D. Do you agree?
Mm-hmm.
So that'll be A plus 6D equals 465. So that'll be A is equals to 465 minus 6D. Notice in this equation we have two unknowns. If you have two unknowns, you need two equations to solve it. Okay? Two
Mm-hmm.
unknowns means you need two equations. We have one equation right here. A is equals to 465 minus 60. Okay, now we're going to use the other piece of the information. T13 equals 219. What does this become on the left side? On the right side, it'll stay as 219. What does it become on the left? Ideas.
A plus 12D.
A plus 12D. Now you can either use elimination, right? You have a system of linear equations here. So you could use elimination or you could use substitution. Um, both works. I prefer elimination. They will look like this. A plus 6D is equals to 465, and then you have another equation. Do we add or subtract them?
Subtract.
Subtract. So you get 6D is equals to minus 465, so that'll be negative 246. So D is equals to negative 41. So D is negative 41. How do we get A now that we know D? Just plug it in there. Okay?
Mm-hmm.
That means A is 465 minus 6 times negative 41. So that'll be plus 41. So 465 plus 6 times 41, 711. So A is your 711, and now we can finally answer the question. A is going to be 711. D is negative 41. So for T100, are we expecting it to be lower than 219 or more than 219? Look at the pattern here.
Lower.
Lower. So if we get a number bigger than 219, something went wrong. 3348 is the final answer. So your 100th term in this sequence is negative 3,348. And you're done. Cool?
Mm-hmm.
So this is going to be your bread and butter for arithmetic sequences. And this question is very, very common. It's not terribly difficult because you're just solving a system of linear equations, which is like grade 10. Um, let's look at a word problem because word problems are always going to be more difficult. So a student plants a seed. After the seed sprouts, the student monitors the growth. Okay, so we're monitoring the height every week. The height after each of the first 3 weeks was 7. So we have week here, and then we have the height. So in week 1, 2, 3, 7, 20, 33. If this pattern continues, in what week will the plant be more than 100 millimeters tall? What's the question asking us? I'll give you the formula. You tell me what's the unknown here.
N.
N is the unknown. What is A?
It's 7.
Yes. What's D?
Is it 13?
D is 13. Yes. Do we know anything else? What is that?
That's 10.
That's Tn. Like that, right?
Mm-hmm.
Now we have everything. Tn is 100. A is a 7. And we don't know. D is 13. So now this is just a simple linear equation. 93 divided by 13 is n minus 1. So n is, does 93 even go to 13? Nope, something went wrong. What is it? Oh, it says more than 100 millimeters. Okay, okay. So it doesn't have to be exactly 100, okay?
Mm-hmm.
So I get 7.15. So now the question is, how do we answer the question? Let's see at week 7, because our n value is 7.15. Let's see at week 7. I'm just going to plug 7 in here. So ignore the 100. We're just going to plug 7 in there. 7 plus 6 times 13. So in week 7, the height was only 85. So what's the answer to this question? 7 or 8?
8.
8. So the final answer will be in what week? The 8th week. Okay?
Mm-hmm.
And that's the final answer, and we're done. So that is arithmetic sequence. 7i, it says determine whether the sequence is arithmetic or it's geometric. Let's look at A, 5, 15, 45. Is that arithmetic or geometric?
It's geometric.
Okay, how do you know?
We're multiplying.
Yeah, we're multiplying by 3, right?
Mm-hmm.
So here for this one, we know it's a geometric sequence. The formula for geometric sequence is slightly different. So for arithmetic, it was Tn equals A plus n minus 1d. For geometric, it's Tn is equals to A times R now to the power of n minus 1.
Mm-hmm.
So it says find T6. How do we find T6?
Is R like the number we're multiplying by?
R is the common ratio, so it's going to be T2 over T1. I like how here D is T2 minus T1. So
Mm-hmm.
here it's going to be 3.
Okay.
So it'll be 5 times 3 to the power of 6 minus 1, right?
Mm-hmm.
It's going to be 3 power 5 times 5. 12, 15. There we go. Easy peasy. Let's say the question asked you for recursive. What will be the recursive for this, for part A? How do we get the next term in terms of the previous? So you take the previous term. What do we do with it? How do we
We
get,
multiply it.
yeah, you multiply it by 3.
3.
That's it. There you go. That's recursive. Easy peasy. You understand that?
Mm-hmm.
That's all there is to this. I'm gonna waste time with more of them. This is gonna be tricky, I think. We're not gonna do the first 5 terms thing. We can ignore these as well. Let's try this one. So it says this is a geometric sequence. Determine the recursive formula and the general term. For a geometric sequence, Tn is going to be A times R to the power of n minus 1. Do you remember seeing this formula in class for arithmetic?
Yeah, I remember the first one.
Is it the same letters?
Yeah.
So I guess you'll also be seeing the R. So we don't care about the arithmetic here because it says it's geometric. So this is the formula for the general term. But here, we don't know what A is. We also don't know what R is. But we do know that T2 is 36 and that T3 is 144. Um, okay. We know the second term. We know the third term. How do we find R? Remember? How was it that we found R, the common ratio?
144 over 36.
Yeah. So here it's easy because they are consecutive numbers. Like that. That has to be 4. So R is 4. Let's look at this one. So T2 will be A times R, 4 to the power of 2 minus 1, right?
Mm-hmm.
And T2 is 36. So we have A times 4. 2 minus 1 is 1. So that means A is 9. What do we need? We need the recursive formula in the general term. Okay, the general term is Tn equals A times 4 to the power of n minus 1. What's our recursive?
It's Tn times 4.
Yeah, you're done. Easy peasy. So here it's a little bit easier because they were consecutive numbers. But you'll see that they're not always gonna be consecutive. Let me see if there's a question on this. Hmm, don't see it. Okay, maybe this one. Let's say we see this question. Does it say geometric? It better say geometric. There it does. So we're given the information that this is a geometric sequence. Recursive is just d times tn, so we can ignore that. The question is, what's the general term for this sequence? So tn is a times, actually even this is pretty easy now that I look at it, because a is given in the question. So let's just solve this. So a is 42. T9 is 2112, right? A is 42, so I'm going to replace this with this. So 42 is A, R we don't know yet. N we do know it's 9 minus 1 equals 2112. So let's divide both sides by 42. So 2112 divided by 42, that's going to be some number. Okay. How do I solve this for R?
You do the eighth root.
So you do this to the power of 8. Why is this not divisible? So the R value here is just weird, which is fine. To the power of 1 divided by 8. So you get an R value of 1.63, and from here it's easy, right?
Mm-hmm.
You can just plug it in. So this is not that hard, actually. All right, so that's just an intro quickly into sequences. Let me just show you what I mean. When it's not possible to write everything as a general sequence, what would that be? That would be 7.3. Let me just find it. Maybe something like this. Yeah. See if we can even write it as a general form. Let's look at this one. Now, I'll just tell you that this is neither arithmetic nor geometric. The resolution is terrible. Let's see, this is the question. Question is like, write the general form if possible. If not, give us a recursive. You'll see that general is not going to be possible here because your D between these two is a 9, right? Between these two is 26. So your D is already changed. This is not arithmetic. What about geometric? Could this be geometric? For it to be geometric, the ratios, right? These, the next term over the previous term, all have to be the same. This is 2.8. Is that 2.8? I don't think so. Let's try it. 41 divided by 14 is 2.92. 122 divided by 41 is going to be 2.97. It's approaching 3, but it's not consistent. The R is not consistent. So this is not a geometric sequence either. So that means we cannot come up with a general formula for this sequence. So the only way we can write this is by using a recursive formula. And recursive relies on patterns. With arithmetic and geometric, it's very easy. But something like this, it's not as obvious. Do you see the pattern here? I'll give you a hint. It has something to do with multiplying by 3. There's more to it. See if you can spot the pattern. How do we get the next from the previous?
You also have to subtract 1.
You also have to subtract 1. There you go. That's it. That's the pattern. So what will be Tn plus 1? How do we get the next term from the previous one?
You multiply and then add 1.
Yes, so it'll be 3 times the previous term minus 1. Okay,
Mm-hmm.
as an example here, this is T2, T3. T2 will be 3 times T1 minus 1, so 3 times 5 minus 1, 14. T3 will be 3 times T2 minus 1, 3 times 14 minus 1, 42 minus 1, 41. So recursive is useful in these cases where the pattern, where you can't write it in terms of the general form. Okay?
Mm-hmm.
Okay, that's enough of that for now. We'll do more of it next week. So for the rest of the lesson, let's do something else. You'll notice that I've changed the book because the other one doesn't have as many questions. Let's look at this one. First of all, let's recap what we've been doing. We've been finding the integral, which means the area. And we've been doing this because to find the area of a curve, it's not really possible to do it by hand, right? If it's a straight line, yeah, you can triangle it. You can turn it into triangles. As long as it's a straight line shape, you can turn it into triangles, rectangles, get the area. But for curves, that is not possible. So we use integrals to find the area underneath the curve. So when it comes to integrals, some of them are very obvious, like the integral of x is x squared over 2 plus c if it's indefinite. It's just a polynomial. For these guys, it's very simple. You just add 1 to the exponent and you divide by the new exponent. So this is just called simple integration. But at other times, such as the question right here, this direct integration will not be possible because there is a chain rule component to this, right? You'll see that this x, where does this come from? This comes from the fact that when you take the derivative of this, you'll have to multiply it by 2x. The constants are redundant. You can always add, multiply any number to get the constant. But the most important part here is that when you take the derivative of the inner bracket using the chain rule, you'll get an x there. That's where this x comes into play. Now the question is, how do we integrate it? Direct method doesn't apply. So if you see this pattern, right? If you see that the outer function is a derivative of the inner function or something like this, the best thing to do is to use substitution. We are going to use substitution. Now the question is, what is u? Is it x or is it 1 plus x squared? u is always going to be the function that you differentiate.
So 1 plus x squared.
Yeah, the function that you differentiate to get the other. So here
Mm-hmm.
making 2x or x as u wouldn't make sense. So you have to make u 1 plus x squared. Now we're going to take the derivative on both sides with respect to the variable on that side. Here there's an invisible 1. The derivative, no, it's 1u, sorry. So the derivative of u is a 1. But since we're taking it with respect to u, there's multiple variables here. We're going to call this 1 times du. What's the derivative on the right side of the equation?
2x
2x. What is it with respect to?
dx.
Dx. So if I write WRT, I'm talking about with respect to, okay? With respect to, this is a math terminology. So here that's with respect to dx. Now, this is an indefinite integral, so we don't have to worry about the bounds. Oh, actually, there's one last thing we need to do. So what is dx now? Because we're going to replace dx. Well, dx is going to be du over 2x, yeah?
Mm-hmm.
Now what we do is we replace dx with this, and we replace 1 plus x squared with u. So our our integral becomes 2x, we haven't touched the 2x, times square root of simply au times du over 2x. Now these constants, you can pull them out, right? Constants, they're very easy to deal with. You can always add or divide any number. But here they just cancel out, so you don't even have to worry about it. Look at this. 2x and 2x cancels out. So now all we're doing is taking the integral, I'm going to make this easier. We're taking the integral of u to the power of 1 over 2 with respect to u. So what is going to be the integral of u power 1 over 2? Remember, you're always adding 1 to the exponent. No, we're adding 1 to the exponent. So this becomes 1 over 2 plus 1, 3 over 2, right?
Mm-hmm.
Here's a trick for these things. You're always going to be dividing it by the new exponent. If you have, what is this? X to the power of n, the integral is going to be x to the power of n plus 1 over n plus 1. Okay?
Mm-hmm.
So when you do this, there's going to be a plus c, and you know how to do this. The 2 is going to come, okay, actually, is it going to come to the top or to the second level? Where's the 2 going to go? There are 3 levels. Any ideas?
Second level.
The second level is correct. When in doubt, right? With things like these, always sketch it out. So you have a divided by b over c. You can rewrite that as a divided by b over c. Change that into a multiplication. You have to flip the thing, okay?
Mm-hmm.
So the 2, as you can see, the 2 is c in this case. It's going to go all the way to the top. So it'll be 2 over 3 u, 3 over 2 plus c. But here's the thing. There's no u in the question. That's just something that we introduced. So we have to take it away. We have to replace u with what it actually is. So in this case, u is 1 plus x squared. The question is in terms of x squared. So our final answer, 2 over 3, 1 plus x squared to the power of 3 over 2 plus c would be the final answer. Okay?
Mm-hmm.
And you'll see that when we take the derivative of this, we're going to get the same thing that we had up there. So the derivative of this, 2 over 3 stays as it is. The 3 over 2 comes in the front, times 2 over 3 stays as it is. The inner function, it stays unchanged. Take 1 away from the exponent, and then the chain rule component, 2x. 3, 3 gone, 2, 2 gone. So you get 2x, 1 plus x squared. And that was the question that we had up there. So with integrals, you have this lifeline at the end that you can always double check your answer. It doesn't apply to differentiation, but when you're taking the integral, you can always differentiate it because taking the derivative is always easier. That's just a fact. It's always easier than taking the integrals. You can always check whether you've done it right. Cool?
Mm-hmm.
This one looks a little bit tricky as well. So for this, know that the derivative of cos is a sine. Sorry, not the derivative, the integral of cos is a sine. Because the derivative of sine is a cos. So that's all you have to know for this. It's not that difficult. So again, you'll see that in here, the x cubed and the x4 are related, right? If you take the derivative of one, you get the other. You see that?
Mm-hmm.
Yeah, there's going to be 4 in the front, but that 4, we can always deal with it later. So is this a u substitution question or no? So this is a u substitution question. Whenever you have a derivative, right? You see x cubed as a derivative of x4. It's probably a u substitution question. Okay?
Okay.
So what's our u?
It's x to the power of 4 plus 2.
Right. So the derivative would be 4x3 dx, right?
Mm-hmm.
And dx is du. Again, this is just algebra here over 4x cubed. From here, the problem becomes much easier. So x cubed, we haven't touched it, but it's going to get canceled out anyway, so we're not too worried about it. Cosine of what? What goes after cosine here? Remember, we're just doing a substitution, so we're replacing that entire bracket with what? With the
With
letter,
dx.
with the letter u. Okay?
Mm-hmm.
With the letter u. And what do we replace dx with? See right here.
With u over
Yeah,
4x3.
du over 4x cubed. From here, it's much easier. So x cubed, see you later. The 4, you can always pull it outside of the integral. Any constants, you can always pull it outside, so you don't even have to worry about it like that. What's the integral of cosine?
It's sine.
Sine. So your answer is 1 over 4 sine u plus c. Remember, for indefinite integrals, when there's no bounds, you always have to add a plus c. But again, the final step, there's no u in the question. We have to replace this back, right? There we go. That's going to be the final answer. Did that make sense?
Mm-hmm.
Is this difficult?
No.
That one's not that hard. Let's try this one. Okay, what's the approach here? Is this a u substitution question or no?
It is.
How do you know? Because that x in the numerator, right, is a derivative of what?
The
Is it
denominator.
the denominator, 4x squared, will give you 8x. But that 8,
Mm-hmm.
again, we can always kill it. So here, our u must be 1 minus 4x squared. Okay?
Mm-hmm.
So what's du? Ideas? What's the derivative of 1 minus 4x squared?
It's 8x.
Negative 8x times, and again, there's two variables here, so we have to be careful with the variable. Again, we've done this a few times. You'll see that it's not that difficult. This is the same thing we did every single time. Now here, I'm just going to replace this with this, right? And dx with du over 8x. Do you see it? This entire
Mm-hmm.
thing is u, right? And again, things cancel out and we're done. It's not that difficult. So x and x gone. That 8, I'm going to pull it outside. I'm going to do one more thing here, which is that I'm going to move the u up there, like this. Why? Because remember this rule, x to the power of n, or any variable to the power of any number here. It's always going to be, the integral is going to be that exponent, you add 1 to it, and whatever the new exponent is, you're going to divide the entire thing by the new exponent like that.
Mm-hmm.
So what's the integral of u to the minus 1 over 2? You add 1 to negative 1 over 2, which gives you what? See, it's not that difficult, right? Look at this. We're comparing this with this. Look at the n. Added 1. What's negative 1 over 2 plus 1? It's 1 over 2, right? Negative
Mm-hmm.
0.5 plus 1 is positive 0.5, same idea. And then we divide the thing by the new exponent. Well, the new exponent is 1 over 2, so we're going to divide it by 1 over 2. Okay?
Mm-hmm.
Now the question is, does that 2 at the bottom, does it go to the top or does it go to the denominator?
It goes to the top.
Yes. So our final answer, again, we're gonna replace the u, so the 2 goes all the way here. So 2 goes here, 2 over 8 is negative 1 over 4 times u was 1 minus 4x squared, 1 over 2 plus c. There we go. That's going to be the final answer. And like I said before, it's very easy to double check your answers with an integral because you just take the derivative. Now, if you take the derivative of this, hopefully we get this. And let's see if that's the case. So take the derivative, the 1 over 2 comes in the front, so negative 1 over 4 times 1 over 2 times the inside stays as it is. You take 1 away from the exponent, and then the chain rule component here would be negative 8x. Now when you do this, you'll see that 4 times 2 is an 8. This negative sign and this negative sign cancel out, and you'll be left with x times 1 minus 4x squared to the negative 1 over 2, which is this thing right here. So it checks out. This one, we don't even need to do a u-substitution because the only issue we're dealing with, the only concern here is the 5, which is just a constant. Um, Remember the integral of e, right here, e to the x is e to the x. But let's say you have a number in front of the x, then the integral would be this exponent divided by that number, like that.
Mm-hmm.
So what's the integral here?
It's e to the 5x over 5.
That's it. Plus c, done. You don't really have to do a u substitution. I'm sure the book does it, but there's no need to do it here. This one could be really interesting. What about here? This one's tricky. This is where you make your money because it's not as straightforward. Because the derivative of x5 is not x2, right? It's 4x x4.
Mm-hmm.
And here's the approach for this one. Usually, okay, usually, not always, 90% of the time, the complicated looking thing is going to be your u, most of the time. What would be du?
Is it just 2x?
Yes. Okay,
Mm-hmm.
let's keep that in mind. Does that really help us? It doesn't really help us as of right now because there's a trick to this question, and the trick is this. You see this x5, right? We have to somehow make this related to the x squared. Right now, there is a relationship. But what if? And this is, once you know it, you'll be able to start seeing it this way. You can see that this is a substitution question simply because you have a complicated looking function times a polynomial. You're taking the integral, usually the case for substitution. Here's what you do here. This x5, you're going to rewrite that as x times x4. Why? Because the only way we can relate x squared, this u term, to the outside bit is because the derivative of x squared is 2x. So we need an x power 1 somewhere. So that's why we're going to replace that x5 with x times x4, okay? So we can relate x with this. What about the x4? This one's even more complicated. So what you do is you go back here. I can relate x4 to x squared. X4 is x squared squared, right?
Mm-hmm.
So the trick here is this. Again, we'll do this next time as well. U is 1 plus x squared. That means x squared will be u minus 1. Do you agree?
Mm-hmm.
That means we need x4. What would x4 be in terms of u? See, we squared both sides here. X squared to x4, we squared it. That means x4 is going to be u minus 1 to the power of 2. We have x squared. We need x4. We squared this side. That means let's square the other side as well, which means ultimately your problem is going to look like this. It was root u times x5. We know x5 is x times x4, which is u minus 1 squared, okay?
Mm-hmm.
Times dx. Dx is du over 2x, like that. Cool?
Yeah.
Now this cancels out with this. And from here, You open this bracket, you open the bracket, and it's easy from here. Cool?
Mm-hmm.
The hard part here is definitely this one. No one thinks about this one. But you have to be able to relate all the variables you have in terms of that u variable, which only comes with practice. All right, let's call it there for today.
Okay, thank you.
See ya.